This is lecture 6 of solid state physics, and in this we go further from lecture 5, where we developed free electron model for 1 d electron gas and go to 3 dimensions. So, just a quick recall that in 1D I had psi k x equals square root of 1 over L e raised to I k x, and we had applied periodic boundary conditions that gave k equals 2 n pi over L, where n equals 0, plus minus 1, plus minus 2, and so on. And density of states in K was L over 2 pi. And then we introduced ideas like K f, epsilon f, and density of states in the energy. So, now we do the same for 3D. Where the Hamiltonian is minus h cross square over 2 m del square. The momentum operator is h cross over I del, and h and p commute, and this means psi r are simultaneous eigenfunctions of h and p. So, I have h psi equals E psi and p psi equals the operator p momentum psi. So, h, which is minus h cross square over 2 m, del square is minus h cross square over 2 m, partial x square plus partial y square plus partial z square, and by separation of variables you can therefore write the wave function psi as a function k equals some constant e raised to I k x x plus k y y plus k z z, which is c e raised to I k dot r, where k vector is k x I plus k y j plus k z k, and r is x I plus y j plus z k. The momentum operator acting on psi gives you h cross k psi. So, momentum is h cross k for state k. The energy is h cross square k square over 2 m, which is h cross square k square over 2 m plus h cross square k y square over 2 m plus h cross square k z square over 2 m. I am writing it in this particular form for a reason. Then we apply periodic boundary conditions. Again, this is a mathematical device to keep the wave functions as exponential, and in this what we do is we take a cube of side L, and demand that psi x plus L y z be equal to psi x y plus L z be equal to psi x y z plus L equals psi x y and z. And if you look at the wave function, this immediately tells you that k x is going to be 2 pi over L n x, where n x equals 0 plus minus 1 plus minus 2 and so on, just like 1D, and k y is going to be 2 pi over L n y, and k z is 2 pi over L n z, where n z are also 0 and plus plus minus 1 plus minus 2 and so on. So, let me rewrite this on this slide. So, I have my wave function psi k r equals e raised to I k dot r times a constant c, which is e raised to I k x x plus k y y plus k z z, where k x is 2 pi over L n x equals 0 plus minus 1 plus minus 2 and so on, k y equals 2 pi over L n y equals 0 plus minus 1 plus minus 2 and so on, and k z equals 2 pi over L n z equals 0 plus minus 1 plus minus 2 and so on. So, now I have all these points, k points, spread over corners of a cube. Right. So, if I just look at one particular cube, say at the corner of 0, this is a cube, let us say this is x, y, z. So, there is one point at the corner here, which is n x 0, n y 0, n z 0. There is one point at this corner here, which is n x 1, n y, n z 0. One point here, which is n x equals 1, n y equals 1. One point here, which is n y 1, n x and n z 0. Point here, which is n y equals 1, and z equals 1, and so on. These are the points which represent one state, and you can keep building this cube further, just keep piling them up. So, each state at the corner of a cube of size delta k x, delta k y, delta k z equals 2 pi by L times 2 pi by L times 2 pi by L equals 8 pi cubed over L cube has been shared among 8 cubes of the same size, and this implies there is one state for delta k x, delta k y, delta k z equals 8 pi cubed over L cubed volume in k space. L cube is the volume of that cube I had taken real space. So, this is 8 pi cubed over V in k space. So, density of k points is equal to L cubed over 8 pi cubed per unit volume of K space. So, if I look at this K space and if I take some arbitrary volume delta V, let me say in K space, then the number of states in this would be L cubed over 8 pi cubed delta V K, which is V over 8 pi cubed times delta V K. Now, normalization of the wave function. Is done over the cube of side L. So, that means integration psi k mod square d v is equal to 1 gives me c square times L cubed equals 1 or c equals square root of 1 over v. So, the wave function for free electrons in 3 dimensions is going to be psi k equals square root of 1 over v e raised to I k dot r, where k is equal to 2 pi over L inside n x I plus n y j plus n z k. So, we have now defined the wave function for free electrons in 3 dimensions, and if I were to represent it in this n space, let us say this is n x, n y, n z. There is one state when everything is at the center, one state at 2 pi L removed. Then I form this cube and one state at each corner. Then I extend this further and there is the state at this corner also. I am making them really large, but these distances are 2 pi by L. So, they are very small. Then I can extend this further up here. I will just make a few and then and here are these states here again. And volume of each cube is 2 pi by L cubed or 8 pi cube by L, and it contains exactly 1 K state, which means by Pauli exclusion principle 2 electrons in each of these states. Since they are close by, let me just make a 2-dimensional representation of it. Suppose I just take n x and n y, they are really all very close here, and then energy depends on k square. So, as you go far away, it becomes circular in 2D and spherical in 3D, because energy E is equal to h cross square over 2 m k x square plus k y square plus k z square, which is h cross square over 2 m 2 pi by L square nx square plus ny square plus nz square. So, these are degenerate. Nx square plus ny square plus nz square equals sum is n square are degenerate states. As long as this number is the same, you get the same energy, and therefore, if I go back to 3D, all those cubes, they give you these energies very close here. The constant energy surfaces are going to be these spheres. And these states are spread inside. All over. So, number of states between k, now k I will mean the radius k, and k plus dk are equal to, the volume in the k space is going to be 4 pi k square dk, and we have seen that per unit volume of k space the number of states is V over 8 pi cubed. So, this comes out to be V over 2 pi square k square dk, and this means number of electrons in these states is going to be equal to 2 for the spin times V over 2 pi square k square dk, which is V over pi square k square dk. If number of electrons is equal to n and highest occupied level has wave vector k f, which I call the Fermi wave vector, then I have n equals V over pi square integration k square dk 0 to k f, which is equal to V over 3 pi square k f cubed. So, I get n equals V over 3 pi square k f cubed, or n over V, which is the number density of electrons, is equal to k f cubed over 3 pi square. Fermi wave vector is going to be 3 pi square n raised to 1/3. So, just like we did in 1D, now we have found the relationship for Fermi wave vector in 3D. The Fermi energy is going to be epsilon f, which is h cross square k f square over 2 m, which is h cross square over 2 m 3 pi square n raised to 2/3. How about the average energy per electron? Again, if I look at this sphere, of radius k, between k and dk, I have number of electrons, which is 2 times V over 8 pi cubed times 4 pi k square dk, and energy of each is h cross square k square over 2 m. And I need to integrate this from 0 to k f and divide by n, total number of electrons. That is E by n, and that is average energy, and you calculate this comes out to be 3/5 of epsilon f. So, in 3D this is the average energy per electron. And finally, I need density of states, because these states are quasi continuous. I work in terms of density. So, between k and dk I have dn, which is equal to 4 pi k square dk times v over 8 pi cubed. These are the number of states, and I want to calculate dn de, which will be equal to v over 2 pi square k square dk de. Density of states per unit volume, I will divide by volume on both sides. So, I get d n over v over d epsilon, which I will write as density of states d epsilon. It will be equal to 1 over 2 pi square k square dk de. So, I have got de, which is number of states per unit energy range per unit volume is equal to k square 1 over 2 pi square dk de. E is h cross square k square over 2 m. You substitute all this in and you get de equals m over pi square h cross cube square root of 2 m e, proportional to epsilon raised to 1/2. So, in 3D density of states is proportional to epsilon raised to 1/2. Now, let us get a feel for some numbers. For metals, I have n roughly equal to 10 raised to 30 per meter cubed, k f, which is 3 pi square n raised to 1/3, therefore, would come out to be roughly 10 raised to 31 raised to 1/3, which is about 1.4 times 10 raised to 10 meter inverse. The corresponding wavelength lambda f, which is 2 pi over k f, is of the order of angstrom. The Fermi energy epsilon f in metals is h cross square k f square over 2 m, which is 10 raised to minus 68 times 10 raised to 20 divided by 10 raised to minus 30, that is 10 raised to minus 18 joules, or of the order of 10 eV. So, you can say epsilon f would vary from say 1 to 10 eV. Density of states, there are roughly n states in range of 1 to 10 eV. So, I can say that dE is of the order of 10 raised to 30 by 10, 10 raised to 28 to 10 raised to 29 per unit energy volume. That is the density of states we are talking about. Now, once we have done all this, we have developed this whole thing, what picture emerges is that in 3D, I have all these states. If I were to plot this in terms of k x, k y, k z, up to k f filled, the corresponding energy is epsilon f, and now when I put this in some temperature, and that means kBT of the order of 25 MeV, just like what happened in 1D, very few states from the top because total number of states of the order of 10 raised to 28, 20 raised to 29. kBT has very few states, these will be able to participate in this thermal process. So, again what is going to happen is number of electrons participating will be of the order of kBT. Energy of the order of kBT. So, CV will again come out to be T, just like in 1D. Again the same principle applies, that because of Pauli exclusion principle, the electrons from inside cannot get excited by thermal energy. Only very few right from the top get excited. Take that energy kBT and give you this answer. Now, what we will do in the next lecture is how do we calculate this exactly. To do that, what we need to do is, you see at 0 temperature, all the electrons are filled up to this epsilon f. I am now giving epsilon, the energy, versus occupation. This is the Fermi Dirac distribution. As you raise the temperature, and I am going to exaggerate a bit, this fellow changes its behavior and it becomes like this. The electrons from this region out here leave the Fermi sphere and go higher energy. This is roughly kBT energy from the range kBT of energy, and they gain energy. So, energy change is going to be given by the new energy E nu at T is going to be integration dE, that is the density of states. Each is occupied by this Fermi Dirac probability. Let me write this Fermi Dirac at temperature T dE and with energy E. E old was n times the average energy 3/5 epsilon f. I can also write this as integration dE f f d at t equals 0 E dE E. Anyway, E, this is 1 up to epsilon f and then 0. So, this gives you the same answer as this. And then what you need to do is calculate dE at t, which I have written as dE nu divided by dt, and that will give you CV. I have already argued this is going to be proportional to t, but we will do the exact calculation in the next lecture. So, let me conclude this lecture by saying that we have developed 3D free electron model and given Kf, epsilon f and dE for it. Thank you.